Welcome everyone to the workshop. For joining us here today. In the next 30 minutes, I will give you a brief introduction to quantum algorithm design automation and the main motivation for us why we are organizing this workshop. And I'll end with an overview of what we have for the workshop. I'm Aritra Sarkar, and I am a postdoc in the quantum machine learning group at QuTech and Delft University. And we're organizing this workshop with Sebastian Feld, also from the same group, and Thomas Lamar from Bellevue, Germany. Yeah, so let's think about what algorithms can do for you nowadays, and it's quite incredible. Yesterday, I was just going around in the supermarket, and this this is cola flavored, which has been designed by AI. A Dio, which has also been designed by AI. Yeah, but can can AI also automate quantum algorithm design? Yeah, it can design a cola, it can design a Dio, and that's what we are going to look at today. And I'll start off with a question that we asked in a workshop last year at IEEE Quantum Week. Uh, we gave a tutorial on machine learning for quantum computing. And let's start off with the question on how many quantum algorithms are there? And these were the options that we did, 1, 10, 100,000. The reason why we asked this question, of course, I'm not asking you all today, is that this question can be looked at from multiple different perspectives. And all of them seems to be right answers. So if you're thinking of the grand institution of quantum algorithms, just one single quantum algorithm, the quantum singular value transformation, which if you tune the parameters, you can get Groover search, HHL, or QFT from it. This, like the most popular quantum algorithms, they are about 10 or 20, all from like big guys. Also, there's like the quantum algorithm zoo, and you'll find somewhere around 400, 500 algorithms there. And yeah, they also count as quantum algorithms. That's why they're in the zoo. And if you have been like attending the IEEE Quantum Week, going to different talks on quantum algorithms, you find that well, grad students, researchers, and companies are also working on different solutions. And there are like thousands or tens of thousands of them. Of course, they also count as different or new quantum algorithms. So now let's look at how quantum algorithm design looks like, and we are going to look at like one of the most famous ones from the textbook algorithm. We're going to look at how, let's say, Peter Shor designed his quantum algorithm. So last year, he had this video on the Qiskit YouTube channel where he talks about the design process that went through in the Shor's algorithm. And then there's like a monograph based on that, which kind of design like talks about the design process in more detail. And the underlying story was that he had this like insight from Simon's algorithm, which was about finding periods in a lattice. And when he was like reading through it, he kind of got this idea that discrete log can be formulated as a period on a torus. And that's kind of led to the discrete log algorithm and later on the factorization of the Shor. So the basic kind of ingredient of discovering an algorithm of the likes of Shor's is basically you need a lot of intelligence and a lot of eureka moves. So it's just not intelligence, you also need some flavor, even for someone. Unfortunately, most of us are, let's say, currently designing algorithms of that level. So how does this process looks like for, let's say, a typical grad student? And I'm going to tell you about my personal story that of designing quantum algorithms. So it was like 2017, and I was doing my master thesis, and this was my like problem statement. Can quantum algorithms accelerate genome sequence reconstruction using a specific quantum algorithm, specific technique called reference alignment? And these were kind of the steps involved in doing that. So first, we start off with what is GSR. I was not from the bioinfo background, so I had to figure out what algorithmic formulations of a GSR is in terms of, let's say, pseudocode. So once you know that, you try to figure out what are the different classical techniques which already exist in solving GSR. Great, you have that, and then you pick out the best, like state of the art in GSR. At that time, it happened to be BWMM. So once you have this algorithm BWMM, you want to look at what are different components in BWMM. And not always they are algorithms. There can be a lot of heuristic components as well. These are like super optimized for industrial pipelines. And yeah, not everything has been formulated and proven rigorously. So once you have these components, then you want to ask, are any of these components suitable for quantum acceleration? For this case, unfortunately, it turned out to be unlikely. So I couldn't figure out a part in BWMM which can be accelerated on quantum theory. So what do I do from there? Kind of realize that, okay, BWMM doesn't work, but if you go back into the algorithmic formulation of GSR, quantum algorithm, the way that you formulate a quantum algorithm for GSR might be entirely different. So that's where the quantum algorithm design process started. So with that, so GSR is kind of like a substring match on the reference genome. So we can formulate it as a Groover search algorithm. Great. And of course, Groover search gives you a provable quadratic speedup if there's like if the data is unstructured, and that's going to revolutionize genome sequence reconstruction theoretically. So by revolutionize, I mean like in GSR, every year the new state of the art kind of improves the previous one by some constant factor. The previous one was a factor of 1, now we have a factor of 1.1. In that case, a quadratic improvement is kind of revolutionary, and it's going to like enable applications which are kind of dreamed of in the classical computation, high performance computation using that. Yeah. And you can do something like you can sequence genomes faster than the in here. So with that, then you need to know how to encode and embed the data in the quantum algorithm. And then there are like I had to study other quantum algorithms for it, like the quantum associative memory and the quantum phone directory, and some mixture of that was used to encode the data. Once you encode the data, you have to kind of make it realistic for specifically genomics data, which are kind of noisy when it comes out of this sequencing machines. And also, like, there's not always a perfect match. So basically, what I was looking for is an approximate partial multi-element search. There are quantum techniques for that, and basically, what I had to do is mix the generalization of Groover search called amplitude amplification and a special kind of oracle called distributed binomial query. Now, well, with all these 5 different things, Groover search, associative memory, phone directory, amplitude amplification, and binomial distributed query, it was kind of like a patch of Frankenstein algorithm. The KeyBAM, well, that worked. I defended my master thesis. It worked super well on paper. The scaling was good. I was able to implement it on a proof of concept quantum simulator for a very short game. But that, of course, left a lot of things to future work. Firstly, how many qubits will it need for a realistic human genome? Then, what's the QPU connectivity? How many actually gates will be required more than the scaling? What's the minimum gate fidelity will be required if there's that many number of gates? What's the coherence time that translates? And with all these factors coming into place, do you still have quantum advantage? And at that time, obviously, the answer is no. But will it ever have quantum advantage? That's like a more realistic question to ask. Yeah, so these things remain open even when we are designing quantum algorithm nowadays. Of course, I went ahead with my work in PhD and designed some more quantum bioinformatics algorithms. Some were based on QPOS, QAOA annealing. Some were based on BQE and energy minimization. But the underlying learning that I had from that is it, it requires certain things to design new quantum algorithms. So firstly, you need an expert training. You have to understand what quantum mechanics is, how quantum computing works. And even with that, they are still counterintuitive. So you have to have this kind of serendipitous moment. Great, you make a quantum algorithm with these two, but then you have to figure out that they cannot be realistically deployed right now. So you cannot test them working with either a big case in a quantum simulator or a quantum hardware. And even if you get them to working, you cannot exhaustively do verification and validation. So like might be a good way to approach quantum algorithm design is by if you can make algorithms which are correct by design. And my other interest was in, well, scientific methods, like just studying about it. And that kind of can be formalized in what's called as universal reinforcement learning. And this is one way to do automated science or automated, in my case, quantum information processing. And what I feel is super nice that we should focus on is interpretable quantum information. Can an agent automatically learn uh, what are the rules of quantum mechanics and design a quantum algorithm based on? So with this correct by design and interpretable, and well, the models can be interpretable or the results can be explainable either way. Um, how do we like start automating a quantum? So the first step when someone tells you to automate a quantum algorithm would be, is it even suitable for quantum acceleration? And that's not an easy question, and that has a lot of theoretical assessment problems in that. And that comes from like supercore quantum mechanics theory and quantum computing theory. The first thing that you need to consider is quantum computing and classical computing are at the same level by Turing degree or the arithmetic hierarchy. So quantum computers cannot do hypercomputation, which means the set of functions that quantum computers can implement is the same for both classical and quantum. So now that means that every time you make a quantum solution, there can always be a classical solution. And that is the first thing that the quantum algorithm has to be a bit faster than the classical simulation. And in many cases, they are not. So there are good classical algorithms which can use quantum algorithms based on the current clock speeds and stuff. And there are also like so where the advantage comes in quantum computing, so that's from the resources that are used in computation. So mostly people study the time resources. And there is a very small space like where quantum is like polynomial and where classical probabilistic computing is polynomial. So that's the BQP minus BQP. And then you have to find out if any of those problems are actually practical in their consistency. So that's a very hard specification. But there can be other resources where it can be valuable. It can be valuable, for example, in generalization or learning or representation capacity. For example, the kernel methods are not specifically based on time speed. So with these two, what becomes difficult is directly from the code structure, you cannot really understand if you are going to get a quantum. For example, if you have a quantum adder, you don't have a speed up, but if it's part of a quantum algorithm, you have to use a quantum adder so that the superposition stays while it is being added. So that's the first point. The second thing is most of the time we don't really care whether it's a PQP problem. Most of the industrial problems are NP hard or in the NP class. And as far as we know from the theoretical side, quantum computers cannot exactly solve NP complete problems. So that's also a focus on exact, and we do not get an exponential speedup. But what we can always get is a polynomial speedup using quantum search, provided that there are no better classical qubits. So there's a lot of ifs and buts in there. So with these two, again, with these two theoretical things, we have different models of quantum computing. So it can be like quantum Turing machine, adiabatic quantum computing, measurement-based quantum computing, and each of them are kind of polynomially related to each other, much the same way that classical computing models like cellular automata or classical Turing, universal Turing machines are also polynomially related. And if the problem is in this BQP slash BQP space, then there is an exponential separation between these two. Otherwise, there might still be a polynomial separation. So now, if you find a solution which is polynomial, which you find has a polynomial speed up on one of the quantum machines, what might happen is this polynomial speed up might disappear in another quantum computing model, or you might find another classical computing model which can also negate this quantum. So that's one of the reasons why in the keynote, for example, yesterday, Krista was talking about focusing more on super polynomial speedups on quantum computing. And the last point is, so the first 3 points were more on asymptotic complexity, but that is again not what industrial advantage focuses on. Asymptotic complexity doesn't make any sense if the problem size or the range of problem size that you have to deal with is beyond, is below your like crossover of quantum technology. So these are already pretty difficult problems to automate. So mostly in this workshop, we will be asking 3 different questions, like how has quantum algorithm been designed so far? How are quantum algorithms represented if you want to automate them? And then how can we actually, what are the different automation techniques used for this? And I'll leave mostly the second 2 questions for our invited talks, and I'll briefly look at just the first question. So how has quantum algorithm been designed so far? And I've kind of classified them into 3 different approaches, but that doesn't mean a single researcher is always using one single approach. They might be wearing different hats for different projects, or different projects might also need a mixture of these. Okay, so the first approach of how a quantum algorithm has been designed so far, I call them the quantum advantage dot theorems. So they start off with the constraints of a specific quantum processing unit. And what they aim to show is a promising use case on that specific QPU. An example would be like solving the protein folding problem using a hybrid algorithm, but then fully optimizing it at the pulse level on a specific QPU with a certain gate fidelity. The focus over here is to extract as much computation power as possible from a certain NIST device. And what's super important over here is to have a solve co-design. And some of the things that we heard a lot in the talks at IEEE Quantum Week is we can do a lot of quantum control automation in this course. And also a lot of low-level compilation can be automated, like circuit optimization. Okay, so then the next approach, in my opinion, is quantum transformation research. So they start exactly from the opposite side. So they start with the problem that they want to solve in the world. That's the industrial use case, and then they tweak an existing quantum algorithm. So that's kind of similar to what I did for the future. Another example would be like you have this satellite image processing pipeline on a convolutional neural network to take one single layer, quantize it. The focus again is on making a small part of a big chain, the quantum kernel, and already fit into an existing application framework. So you have some view of how the future would look like when quantum computers are on scale. What can we automate over here? We can automate the problem formulation. So we can start out with something classical like qubits and stacks and try to translate it to parametric circuits. And we can also look at different ways of data encoding. The third approach is the quantum complexity idealists. So all you have to give these people is a promise that there exist problems which are in BQP but not in BQP, and you give them a set of universal gates for them to calculate the asymptotic speedups. And their aim is to find quantum algorithms that they can prove would have a better speedup. An example would be a super polynomial speedup in determining the zeta function of the genus curve over a finite field. I have no idea what that means. I just took it from the quantum algorithm zoo, so I know the quantum speedup is. So what we are after over here is an asymptotic speedup with respect to best classical algorithms, considering everything else has been taken care of by the engineers. So we have ideal qubits, gates, connectivity, crosstalk, and this. What can we automate over here is we can entirely embed quantum information theory within the agent or the automation engine and try to see if data science. So with these three approaches, we have to look at the quantum algorithm design automation. Kind of made a word cloud of it, of the four things in my opinion which matter. And then I won't be talking into the details of it, and again, I'll leave it to the rest of the speakers. But what I find is interesting to look at is the different interfaces of how do you describe the problem through the automation engine. Then the different representations that the automation engine uses within it to find or make a quantum solution. Then we have the different metrics. Like I said, that only difference between classical and quantum is the resource complexity. So what are the different things that you can measure so that you know that you're going in the right direction? And finally, the different techniques. So for the interfaces part, it can be as simple like a drag and drop quantum circuit like Quark, which has been around for some time. We also have a talk on games, how that can develop quantum solutions. Classical formulations, algorithmic libraries, and DSLs. They're in most of the quantum languages that we have now. And given the popularity, we can also now program in quantum natural language, probably all of it. The different representation again can be super theoretical, like quantum lambda calculus, which might be good for proving programs, or ZX calculus can be used for optimizing circuits. The more familiar ones, assembly code and logic circuits. The low-level things like gate pulses, and again for proving asymptotic complexity, you might look at different metrics. Obviously, like things like fidelity and gate counts are there, but it can also be things like the learnability or how much it can generalize, or more importantly, can be proved that whatever the automation engine is putting out, that will work. And of course, there are a host of different techniques. There's evolutionary computing, there's reinforcement learning, there's symbolic regression, mix of these things like neurosymbolic or neuroevolution. And then we have more things like information geometry and geometric quantum machine learning, where a lot of using. So with that, I'll end the introduction part of my talk. Just to give an overview of what we have in store for the rest of the workshop. In the first session, we have two other talks, and I'll introduce the speaker soon. And then after the lunch, we have again two talks. Unfortunately, Joe couldn't be here from Horizon Quantum Computing. Felt sick and had to go back. And finally, in the last session, we have again two talks dealing with the interface that and how to lower the barrier to entry. Thank you for this part.